This is podcast 4.1 for Mrs. Mahoney's pre-AP chemistry, and we're going to start talking about the periodic table in a little bit more details, looking at some trends and just some relationships within the whole periodic table. So let's just start with a little bit of the history of the periodic table. Clear back to the 1790s, that's when they first made a list of the elements known, and there was 23 at the time. So look at how many we know now, and just think in the last couple hundred years how many advances we've made. And then it was by the next 100 years, 70 elements were known. Now John Newlands is credited for first arranging them, and he arranged them by atomic mass. So he was the first to call them the periodic, like the periodic table, that he was seeing patterns, and that's what it was saying. It was just that it was repeating themselves, and they were starting to see some similarities. And his rows that he started with was it was kind of like turning the periodic table on its side. And so the first periodic table was rows were columns and columns were rows. Then we have Mendeleev and Moseley. Remember the video where they talked about Mendeleev and how the story is that he had cards and he started organizing them by their mass. Or excuse me, by the atomic number. He did it by something else, and he actually did use mass because he did it as a relative mass. It was like everything compared to hydrogen. Carbon was 12 times heavier. Then you can look, calcium would be 20 times heavier. So he really kind of took Newland's work and put his rows into columns. But the big thing he actually made some blanks for what were yet to be discovered. He knew that there were still some more elements out there that he just couldn't find, and the noble gases were some of them. And just kind of a side note, Moseley did the same work. Difference was Mendeleev published first. That's why we know of it as Mendeleev as the father of the periodic table and not Moseley. So if you ever discover something, get it published. So it was Moseley then. He went a little bit further, and he's the one who really identified by the atomic number. And when he arranged it, he started to see a very clear pattern, but it really was using Mendeleev's table, and he really is given the credit for first arranging those periodic table or creating the periodic table. So then we have our periodic law, all nice and formal. Only reason it's written funny and weird like that is to make it look like it's a law. You do not have to copy it like that. But it's just saying that when you do arrange those elements in order of increasing atomic number, there is a pattern. In my afternoon classes that we did the secret agent activity, you guys discovered the patterns yourself, and you have to kind of look not just one-dimensionally, but be able to look in rows and in columns to start to see the patterns. Okay, so now we're going to go back and look at that electron configuration and how is there some similarities when we start looking at that. And I'll come back and reference the configurations, and yes, you can use it to explain some of the chemical properties. And so what we're really interested again are those valence electrons, or those electrons in the highest occupied energy level. That's really going to be our focus that we're going to be looking at from now on pretty much. We don't really worry about the total electrons so much as those valence electrons. Really keep that in mind when we start looking at the CA and preparing for that CA in a couple weeks, because valence electrons are what are the most important. And so they're the ones, because when we talk about losing electrons, gaining electrons, bonding, sharing, that is the valence electrons is what the focus is on. So in your packet you have a little bit of room to the side of that chart. So before we kind of go on about the periods and the energy levels, just remind yourself what that valence electron is. That question was missed quite a bit on that last test, so you may want to rewrite this down and just put itself as a note, or you need to know the difference. And those are my highest energy levels. So now if we look for in electron configuration, they're going to be your last S and P's after that noble gas. But don't forget, we also have the periodic table that can tell us. And why do we care about that? Again, we're going to start bonding after this. We're going to make chemical compounds. Those are the electrons. So when I say it's going to lose 2, gain 2, they're going to share 4. It's the valence electrons we care about. So when sodium loses it, what's it lose? It's 1 valence. And again, remember, they want to be that stable configuration like a noble gas. The Lewis dots. Just a reminder, that shorthand method, I know that we looked at this in class once, but you may want to jot this down in the notes to remind yourself, because again, this can show up on that CA and you definitely need to recognize what it means. So it's just your element symbol, and then for each dot, that's going to be how many electrons we have. Oops, that's my dog Panda. And when you put the dots around it, start on one side, and then you just kind of spread them out because they want to be as far apart from each other. They're all negatively charged, so they want to be as far apart from each other. And again, if you look at it, it's kind of like those orbital notations, how everybody had its own arrow before we doubled back up. Think of it the same way with the dots. Oops. So there, look at the columns again. Down our first. So we're sitting here looking at our first group right here. Everything has 1 dot, 1 valence. Group 2, 2 dots, and we've spread them out. Again, notice we're only talking the main group. We're skipping transitions. Group 13, working our way up to group 18, has 2, 4, 6, 8. This is why they want to gain 1. Everybody here wants to gain 1, because then they'll be like a noble gas. They want to gain 2 to be like a noble gas. They want to gain 1, 2, 3 to be like a noble gas. These guys, remember, metals lose. They're going to lose 3. These guys are going to lose 2. They're going to lose their 1. Plus 1, plus 2, plus 3. The charges, everything comes from the valence electrons. Okay, you had a question then, moving away from the valence electrons. What is the difference between energy level and period? And when we kind of went through and talked about some of the, when we were doing some of the quantum numbers, and we said there's a difference. So look at my first energy level. That color's not going to work. Let's find a different color that might work a little better. So my first period, okay, period. Rows. Okay, I'm talking about the rows. So down 1, 2, 3 on the periodic table. That's my periods. The periods are the rows. I'm an assumption that you know that. You don't know it, write it down. So on my first period, there's only 2 elements, hydrogen and helium. That's the 1s energy level. So look at the same. First period, first energy level. It's the same. Second period, what do I have? I have a 2s and a 2p, 8 elements. It's the same. Third energy level, 3s, 3p, there's only 8 electrons. But there's still more electrons in the third energy level. This is where it starts to change. My fourth period, don't forget, we have a 3d. So in my fourth period, there's actually 2 energy levels being filled in those electrons. And there's a total of 18 elements across it. On the fifth energy level, well, there's also being filled the 5p. It also has 18 elements in the period, but we know that these have a lot more electrons. In the fourth energy level, you actually can hold 32 electrons, and we can actually hold 50 electrons in that fifth energy level. So period is different than energy level. At the 6s, the sixth, what else do I have? I have a 4f and a 5d. There would be 32 elements in that sixth period. Your seventh period, what else do I have? You go down to the 5f's, you have 6d's, you have 7p's. There could also potentially be 72 elements also in that seventh period. So the rows, you're going across, and rows, the periods are different than the energy levels as we're going across. Okay, group names that you need to know. These are names, highlight names. These will show up. I assume that if I'm talking about the alkali metals, you know I'm talking about group 1. They are the most reactive metals. They really, really want to get rid of that one electron, so they're very, very reactive. So reactive, they do not exist in the pure elemental form in nature because they've already made compounds. I would have to chemically isolate it to be able to have pure sodium or pure potassium. Francium is so reactive that we can't even isolate it. Okay, group 2. You need to know group 2 is called the alkaline earth metals. My assumption, you know these names. They're pretty reactive. They are very high reactive, but not as reactive as the alkali metals. These are very soft, very, very reactive with air, with water. Most of these will also react with water, but they're not as reactive in the air. But you also have a hard time finding these free in nature. They tend to be also in the compound form. Okay, over on the other side of the periodic table, group 17, the halogens. They are the most reactive nonmetals. Very, very reactive. You look at they're mostly gases, then we get down to bromine that's a liquid, iodine is a solid at room temperature, but they really, really want that one electron, and they're my most reactive nonmetals. Then you have group 18, your most most non-reactive. They are, add the word that you would also need to know, inert. Another vocab word, inert, non-reactive. Because look at, they don't need any reactions. We used to say zero, but they've actually made some compounds, xenon hexafluoride. They forced it to make some compounds, but that's still not, it doesn't happen in nature. They're very, very non-reactive. And don't forget helium. If we look at helium, this is a 1s2. Sorry, that should be a little 2. But we put it over with the noble gases because of that full outer shell, so it acts like a noble gas in that it has a full shell. Okay, how about the S block, or if we start looking at the blocks, when we just start looking at the similarities, look at your S blocks. They're all metals except, make a note there, don't forget hydrogen is in the S block. Hydrogen looks like it's a group 1. Hydrogen is not a metal. It is not the alkali metals. They don't start until lithium. Hydrogen is a gas, and really its properties are probably, we'd have to say, closer to group 17. Hydrogen's the only one that really can form a +1 or a -1. We really don't know where to put hydrogen. It kind of needs its own little group, kind of a loner when we're looking at it. Look over your P block. This is the most diverse block. We have metals, we have nonmetals, we have metalloids. They become more metallic. Look at what happens as you go down the period. They are becoming more metallic as you go down the group, but it's really hard to say that there's one similar characteristic in your P block. You have a little bit of everything there. Okay, your D's, these are your transition. These are your most stable. This is the most stable metals. Gold, platinum, silver, copper. Very, very low reactivity with the majority of them, which is why we make them as jewelry. You don't want something made out of, let's say, sodium jewelry, because every time you jump in the shower, not a good reaction. We're going to look at a video at that and show us what would happen. I really don't want my gold bracelet to catch on fire every time it gets exposed to air. That's why we use our transition metals. Then we have our F blocks, the lanthanides. Lanthanides are the 4 Fs. They're also called the rare earth series. The actinides, there are 5 Fs. And when we start talking about we start doing nuclear, this is about the only time we're really going to spend much time with the actinides, because there are radioactives, and we'll be using those when we start looking at some of the radioactive decays going on. Okay, let's look at some of those properties then of metals, nonmetals. I'm throwing those words out. These are some properties you need to be able to recognize. So write this down. Metals, they're good conductors of heat and electricity. When we start talking about bonding, we're going to look at why that happens. They share electrons kind of within the atoms, and so there's a flow of electrons that allows for that flow of heat and electricity. Malleable, know this word. Malleable. That means you can roll it or get it into or hammer it into a sheet. You hit it with a hammer, it doesn't break. That's what malleable. That's why you get sheet metal, sheets of copper, aluminum foil, tin foil. Ductile, another vocab word. That's how we get wire. I stretch it and I can get copper wire. Now I say tends to be solid. Really, we only have one. Remember mercury at room temperature. Another word you need to know. Add this. Luster. Metals have luster. What's luster? They're shiny. Metals are shiny, tend to be silver. Remember that video where I have pictures on the wall? Look at all the metals and look at the properties. The majority of the periodic table is metals. Okay, non-metals then. Key word. If you have a gas, you know it's a non-metal. And don't forget the periodic table in the room. Use it. Elements written in the black, those are metals, or excuse me, solids. The blue, only two blues, those are your liquids. Gases are the red. Now nonmetals, poor conductors of heat and electricity. And again, I can have gases, liquids, there are solids. I have much fewer metals than nonmetals. What else do I know about them? Another word, they're brittle. If I hit it with a hammer, they're going to shatter or they'll break apart into other pieces. Whereas the metals, malleable, you hit it with a hammer, it smooths out, it flattens out. Okay, how do I know the difference? Remember that stair step over in the P block? That's what separated it. So my non-metals are over here, metals over here. Then we have our metalloids. Those are the ones that walk the line. They're on both sides of the stair step. And they're the ones that have some characteristics of metals and non-metals. They're all solids. Sometimes they're called semiconductors because they conduct electricity just not as well as metals, but they can conduct electricity. Silicon is used a lot in the computer industry. That's why Silicon Valley in California, because of the computer industry, and it's used a lot in the computers. It's very lightweight. We're actually, Monday in class, you're going to get a chance to look at some of these elements and classify them for yourself. So the last thing on your periodic table, sorry, I forgot I had put this in there. This is where it's the color coding. Blues, metals. The yellows, nonmetals. And again, look at over here. Remember, hydrogen. Hydrogen is your only nonmetal on that side. And then these are the pink. So you may want to kind of color these in. These are your metalloids. So look at aluminum. Even though it's on the stair step, aluminum is a metal, not a metalloid. So boron, silicon, germanium, arsenic, antimony, beryllium, acetine, they are your metalloids. Okay, but you have this chart. Just practice filling this in. So this is what we're going to start with on Monday, and then we will go back and we're going to actually look at some different elements and let you classify by conductivity, by different properties. Is it a metal, non-metal, or is it a metalloid? See you on Monday.